This code snippet imports various Python libraries and performs some configurations that are typically used in machine learning and data analysis tasks involving neural networks and financial data. The library of finance is imported to access financial data, likely for downloading stock market data such as historical stock prices. The SHAP library is a machine learning explainability tool used to understand the output of models. TensorFlow is a deep learning framework used for building neural networks, and here it seems to be configured to use TensorFlow 1.x behavior with tf.compat.v1.disable_v2_behavior, which is necessary for compatibility with the SHAP library at the time of writing. The script also imports NumPy and Pandas, which are fundamental libraries for numerical computing and data manipulation in Python, respectively. Min-max scaler from Sklearn.preprocessing is typically used to scale input features to a neural network. For building the neural network, the script imports sequential from TensorFlow.keras.models, which is used to define a linear stack of layers for the neural network. It also imports various layer types from TensorFlow.keras.layers, including dense, fully connected layers, LSTM, long short-term memory units, and GRU, gated recurrent units, which are commonly used in recurrent neural networks, RNNs, for sequence data such as time series. Additionally, matplotlib.pyplot is imported for plotting, which likely means that visualizations of the data or the model's performance are intended. Lastly, it imports several metrics from Sklearn.metrics, such as mean_squared_error, mean_absolute_percentage_error, and mean_absolute_error, which are used to evaluate the performance of regression models. However, the code snippet does not show the usage or execution of these imports, so it is merely a setup for a larger script that would involve financial time series prediction and analysis using deep learning models, as well as pre-processing steps and model evaluation. The provided code defines a Python class named DataLoader, which is intended to be used for loading and transforming financial time series data, particularly for machine learning purposes. The class inherits from base estimator and transformer mixin, suggesting its compatibility with scikit-learn's workflow, such as pipelines. Upon initialization, the data loader receives a pandas data frame dataset and an integer lag. It then converts the date column of the dataset to datetime objects, assuming an ISO 8601 date format. Additionally, it initializes a min-max scaler instance to scale the data. The get_indexes_split method is designed to split the dataset into training and testing indices based on a given percent for the training size. By default, 80% of the data is intended for training. The fit method fits the min-max scaler to the close prices in the dataset based on the provided indices, preparing the scaler for normalizing the data. The transform method applies a transformation to the dataset to create lagged features. For each data point, it computes a set of new features that represent the close prices from previous time steps, the lag. It then scales these features using the previously fitted min-max scaler and returns both the lagged features and the associated target values in the form of NumPy arrays. The inverse_transform method reverses the scaling operation, converting scaled data back to its original range, which is useful for interpreting model predictions. Lastly, the fit_transform method is a convenience that combines the fit and transform operations, typical for Sklearn transformers. All in all, the DataLoader class is designed to pre-process financial time series data by creating lagged features and normalizing them, so as to facilitate the development of machine learning models for tasks such as forecasting. The provided code performs two main operations related to handling data using the pandas library in Python. Firstly, pd_read_csv/data.csv is used to read the content of a CSV file named data.csv, which is located in the parent directory of the current working directory as indicated by the path /data.csv. The pd_read_csv function is a common way to import data from a CSV file into a data frame, which is a two-dimensional, size-mutable, and potentially heterogeneous tabular data structure with labeled axes, rows, and columns, provided by the pandas library. After reading the CSV file into a data frame and assigning it to the variable data, the second operation data equals data date, close, is a selection operation that filters the columns of the data frame. It reduces the data frame to only include the columns date and close. By doing this, all other columns that might be present in the original CSV file are discarded, and data is updated to contain just these two specified columns. This is typically done to focus on the data that is relevant for further analysis or processing, such as time series analysis on financial closing prices where only the date and closing price columns are required. This code snippet is written in Python and is likely part of a larger machine learning or data processing program. The snippet is creating a data loader object with some dataset data and a lag parameter set to 6. The data loader is assumed to be a custom class designed to handle the loading and pre-processing of the data for a time series or sequence prediction task. The lag parameter of 6 implies that the data loader might use this value to create features based on the lagged observations, which is a common approach in time series forecasting where past values are used to predict future ones. After initializing the data loader, the code proceeds to split the data into training and testing sets by calling the get_indexes_split method on the data loader object. This method probably returns the indices for the train and test datasets. These indices are stored in train_indexes and test_indexes variables. Following the index split, the code segment fetches the training data, x_train and y_train, by applying fit_transform on the train_indexes. This indicates that fit_transform method of the data loader is used for pre-processing the data corresponding to the training indices, likely scaling the features, x_train, and perhaps encoding the target variable, y_train, if necessary. The pre-processed training features and labels are then ready to be used by a machine learning model for training. This code is a Python expression that is likely used to retrieve the dimensions, or shapes, of two variables, x_train and y_train. These variables are commonly used to represent the feature set and the labels, respectively, in a machine learning context. X_train typically contains the input data that will be used to train a model, and y_train contains the corresponding target outputs or labels. When this code is executed, it will return a tuple with the shapes of x_train and y_train. The shape of an array or a data structure in Python, often a number py array or a pandas data frame when dealing with machine learning datasets, tells you how many elements there are along each axis. For example, in a 2D array, the shape will tell you the number of rows and columns. This information is useful for verifying that the data is correctly formatted before it is fed into a machine learning algorithm for training. It can help in debugging issues related to dimensionality mismatches and is often an important step in the data pre-processing phase. The code is using the NumPy library, often imported as MP, to create an array from some existing data, specifically x_train. The np.array function is called with x_train as its argument, which constructs a new NumPy array from whatever x_train might be, a list, tuple, or any array-like object. The type function is then called with the newly created NumPy array. It is used in Python to determine the data type of a particular object. In this case, the type function will return the type of the NumPy array created from x_train. So, the purpose of this code is to create a NumPy array from x_train and then to check the type of that NumPy array to ensure it is indeed a NumPy array, or to see what type of NumPy array has been created, e.g., numpy.array. This could be useful for debugging or for type checking during development. This code snippet performs the function of printing the type of the variable x_train. The type function in Python is used to determine the type of an object, and x_train is the object in question here. When this line of code is executed, it will output the type of x_train, for instance, class numpy.array, if x_train is indeed a number py array. The comment #array suggests the expected type of x_train to be a number py array, which is a common data structure used for numerical data manipulation in Python. However, the comment does not affect the code's execution. It is only there for clarification purposes for someone reading the code. The purpose of this code is to access the first element of two arrays, or other indexed collections such as lists, specifically x_train and y_train. These names usually indicate that they are the training data and labels used in a machine learning context. The x_train array likely contains the features or input variables, while the y_train array contains the corresponding targets or output labels. By accessing the first element of each, x_train 0 for the first feature vector and y_train 0 for the first target label, it suggests that we might be examining or processing the first training example in a dataset. This might be used for various reasons, such as visualizing the data, testing code on a single example, or debugging to understand the structure or contents of the initial training data instance. This line of code is calling a transform method on an object named data_loader and passing it an argument named test_indexes. The transform method is likely designed to process the data referred to by test_indexes in some way, converting it to a different format, scaling it, normalizing it, or extracting certain features, for example. The results of the transform method are being unpacked into two separate variables, x_test and y_test. Typically in a machine learning context, x_test would contain the features of the test data set, i.e., the data that the model will use to make its predictions, while y_test would contain the targets or true labels for that test data. Basically, this line prepares the test dataset for use in evaluating a machine learning model by applying pre-processing steps and splitting the features and labels. The code is attempting to access the shape attribute of x_test and y_test, which are likely to be NumPy arrays or similar array-like structures. The .shape attribute of an array-like structure in Python typically returns a tuple representing the dimensions of the array. For example, if x_test is a two-dimensional array representing test samples with a shape of n_samples, n_features, the .shape attribute would return that tuple. Similarly, y_test is expected to represent the test labels or targets corresponding to x_test, and its shape would typically be n_samples for a simple prediction task or n_samples. N_targets for a multi-target prediction task, with n_samples being the number of test samples and n_targets being the number of prediction targets. Executing x_test.shape, y_test.shape would then return a tuple containing the shapes of both x_test and y_test, giving the user quick insight into the dimensions of the test dataset and labels. This could be used for debugging purposes to verify that the test arrays have the expected number of samples and features before they are used for further processing or evaluation, such as making predictions using a trained machine learning model. This code snippet is likely involved with machine learning data pre-processing. It's calling the inverse_transform method on an object named data_loader. The purpose of the inverse_transform function is to convert the transformed or scaled data back to its original space. Essentially, it reverses a prior transformation. In this particular instance, inverse_transform is being applied to the first 10 elements of an array or list y_train. The y_train variable usually refers to the training labels in supervised learning tasks. These labels may have been previously transformed or encoded to a format suitable for modeling, for instance, scaled to a certain numeric range, normalized, or converted from categorical data to numerical labels. By calling inverse_transform on the first 10 labels, the code is transforming these labels back to their original format, which could be categorical data or their original numeric scale. This could be used for various purposes, such as interpreting the results of a model's predictions after training by comparing with original labels, or simply for reporting or visualization to make the labels human-readable. This line of code is used to set a seed for random number generation in TensorFlow, which is a machine learning and numerical computation library. The purpose of setting a seed with the value 22 is to ensure that the operations which rely on random number generation can be reproduced exactly. This is important when you want to have deterministic behavior in stochastic processes, such as when you initialize weights in a neural network or when you shuffle data for training. By using the same seed, you ensure that each time the code is run, even on different machines or at different times, the random numbers generated are the same, which is helpful for debugging and for comparing the results of different runs or models. The provided code snippet defines three different predictive models, a GRU model, an LSTM model, and a baseline model, which are likely to be used for time series forecasting or sequence prediction tasks. The first function GRU_model creates a gated recurrent unit, GRU, model with 128 GRU units and expects input data with a feature window specified by look_back. The output_window parameter indicates the dimension of the model's output layer, which is a dense layer. The model is compiled with the Atom optimizer and uses mean squared error as the loss function. The second function LSTM_model creates a model with a bidirectional long short-term memory, LSTM, layer. This implies the model processes the sequence data in both directions, forward and backward, potentially improving its context understanding for forecasting. It also features 128 LSTM units and employs an output dense layer tailored by output_window. The ReLU activation function is specified for the LSTM units, and similarly to the GRU model, it's compiled using Atom and mean squared error. The third function, baseline_model, generates a simple heuristic prediction that uses the last known value from the y_train data and extrapolates it across an output window of length output_window for all test instances in y_test. This model doesn't learn from the data but provides a naively constant forecast. Finally, the code initializes the output_window variable for the output dimensions of the models and creates instances of the GRU and LSTM models by passing the output_window and a lag feature derived from a data_loader, an object not defined within the snippet. These models are presumably intended to be trained and evaluated on time series data. The code snippet is a part of a script that trains and evaluates two different types of recurrent neural network models, namely a GRU, gated recurrent unit, model, and an LSTM, long short-term memory, model, as well as a baseline model, on a dataset. It begins by training the GRU underscore model for a single epoch on the training data X underscore train and Y underscore train, with a batch size of 64. It prints GRU underscore model followed by a line of 50 asterisks before the training starts, likely to signal the start of training for that model in the console output. After training the GRU model, it performs the same operation with the LSTM underscore model. Printing LSTM underscore model followed by a line of 50 asterisks before training it on the same training data for one epoch with a batch size of 64. Once both models have been trained, the code uses each model to predict outcomes on the test data X underscore test. The GRU underscore model predictions are stored in GRU underscore predictions, and the LSTM underscore model predictions are stored in LSTM underscore predictions. Finally, the code calculates some baseline predictions by calling baseline underscore model, output underscore window, Y underscore train. This suggests that it is using another model or method, referred to here as baseline underscore model, which probably serves as a comparison to evaluate the performance of the GRU and LSTM models. The code does not show where and how baseline underscore predictions is being used later. This code appears to be part of a larger program, probably related to time series prediction or forecasting using machine learning models like GRU, gated recurrent unit, and LSTM, long short-term memory, which are types of recurrent neural networks. Additionally, there seems to be a baseline model for comparison. The purpose of this specific code segment is to transform the scaled predictions made by the GRU model, the LSTM model, and a baseline model back to their original scale. The predictions generated by these models are likely in a scaled format because it is common practice to scale data before feeding it into neural networks to help with the training process. Data_loader.scalar.inverse_transform is a function call that applies the inverse of a previous scaling operation. It takes the predictions which are in a scaled format, the predictions are reshaped to conform with the expected input shape of the function, and converts them back to their original scale, which makes them interpretable in their real-world context. Each line of code is performing this inverse scaling action for the predictions from the three different sources, GRU underscore predictions, LSTM underscore predictions, and baseline underscore predictions. After this operation, GRU underscore predictions underscore real, LSTM underscore predictions underscore real, and baseline underscore predictions underscore real will hold the predictions in their original scale, which can then potentially be compared to actual observed values from the dataset or used for further analysis or reporting. This line of code is querying the shape attribute of an object named X underscore train. The object is likely to be an array or data structure that holds the training dataset used in machine learning or data analysis. The purpose of .shape is to return the dimensions of the array. It tells us how many rows and columns are in X underscore train. For example, if X underscore train is a two-dimensional array representing features and samples, .shape would return a tuple where the first number is the number of samples, rows, and the second number is the number of features, columns. This is useful for understanding the size and structure of the training set before feeding it into a machine learning model or for debugging purposes to ensure that the data is in the expected format. This line of code is calling the shape attribute on an object named LSTM underscore predictions. The shape attribute is typically used on array-like objects, for example, Python lists, NumPy arrays, or pandas data structures, to get the dimensions of the array. The purpose of this .shape call is to retrieve the size or structure of the LSTM underscore predictions data. It will return a tuple representing the dimensions of the LSTM underscore predictions, where each element in the tuple indicates the size of the corresponding dimension. For instance, if LSTM underscore predictions is a two-dimensional array, shape might return m, n, where m is the number of rows and n is the number of columns in the array. The code snippet data_loader.dataset is typically used in the context of machine learning and data processing, where the data_loader is an object that handles the loading and batching of data from a dataset for a learning algorithm. In this context, .dataset is an attribute of the data_loader object, which refers to the dataset from which the loader is fetching data. The dataset itself usually contains the features and labels required for training or evaluating a machine learning model. By accessing data_loader.dataset, one could inspect properties of the dataset, such as the number of samples, the structure of the data, transformations applied, and other metadata, depending on the implementation of the dataset object. Although the code is short, without additional context it's not possible to specify what operations are being performed on the dataset or how it is being used after this line of code. However, in general, this line of code is used for referencing the underlying dataset associated with a data loader in a machine learning pipeline. The code snippet provided is for parsing dates from a dataset and converting them into a consistent datetime format using the pandas library in Python. Specifically, the first line, which is commented out, indicates an attempt to create a new column called data_parsed in a pandas data frame called landslides. The new column is supposed to contain datetime objects that are generated by converting the strings in the date column of the same data frame using the PD to underscore datetime method, with the format specified as %m/%d/%y, which corresponds to dates formatted with the month, day, and year in 2-digit forms. The second line of code, which is also a comment and is not executed, suggests a more complex operation with similar goals, but there are potential issues with it since it refers to data_loader.datasetDate, which seems to be a different data frame or structure than landslides. Furthermore, it contains a lambda function to apply the conversion to each element in the date column and ambiguously references ISO 8601, which is an international standard for date and time formatting. It appears to be an incomplete snippet of code, and the ISO 8601 does not match the standard Python datetime formats used in PD to underscore datetime. Both lines being commented out means the actual code is inactive and would not perform any operations if run as is. To have an effect, one would need to uncomment the desired line and ensure that all referenced data structures and columns exist and have the correct data that can be parsed with the specified formats. The code data_loader.get_values appears to be a method call in some programming language, such as Python. The purpose of this code is to invoke the get_values method on an object named data_loader. This method, by its naming convention, suggests that it retrieves some values from the data_loader object. The details of what values are retrieved and how they are processed would depend on the implementation of the get_values method within the data_loader objects class. The get_values method could, for example, be used to query a database, read data from a file, fetch data from an API, or just return a set of values stored in memory. Once this method is called, it is expected to return a result, which could be in various forms such as a list, a dictionary, a data frame, or any other data structure that the method is designed to output. The given code snippet appears to be Python code utilizing TensorFlow and the SHAP Shapley Additive Explanations library. The commented out lines suggest options to enable TensorFlow v2 behavior or disable eager execution in TensorFlow v1, but they are not active parts of the code as they are commented. The active part of the code takes a subset of a training dataset x_train by selecting the first 100 samples and creates a copy of that subset to store in sample_train. This subset is likely being prepared for use as background data when explaining the predictions of a neural network model, specifically a GRU, gated recurrent unit, model. The GRU_explainer is a SHAP deep explainer object, which is being created to produce explanations for the predictions made by the GRU model, referred to as GRU_model. The explainer uses the sample_train as background data in order to understand the model's behavior. Deep SHAP is a high-speed approximation algorithm for SHAP values that uses a deep learning framework. It is designed to provide insights into the contribution of each feature to the model's predictions. The comment in Portuguese at the end of the snippet suggests replacing 10 with the desired number of examples for the baseline, which indicates the user should adjust the number of samples if a different number of examples is needed for explaining the model predictions. However, this comment does not actively affect the code's behavior as it currently stands. This code snippet appears to be part of a Python program, which uses SHAP Shapley Additive Explanations to explain the output of a GRU, gated recurrent unit, model. SHAP is a tool for explaining the contribution of each feature to the prediction of a machine learning model. Initially, a copy of x_test is made and stored in the variable sample. x_test likely represents the test dataset, and the copy is created to ensure that the original dataset isn't altered during the SHAP value computation process. Next, SHAP values are computed for the sample using a GRU_explainer, which is an object probably previously created to explain the GRU model. GRU_explainer.shap_values, sample, calculates the SHAP values that quantify the contribution of each feature in the sample to the model's predictions. Finally, shap.summary_plot is used to generate a summary plot of the SHAP values. The plot visualizes the contributions of each feature. Data_loader.inverse_transform is applied to both the SHAP values and the sample, which suggests that the data may have been pre-processed or scaled before being passed to the model. And now we are transforming it back to the original scale or format for better interpretability. Feature names from data_loader.get_values. Columns are provided to the plot to label the features appropriately on the x-axis. This visualization helps to intuitively understand which features are most important for the model's predictions. The code snippet provided is for visualizing the feature contributions to a prediction made by a machine learning model using SHAP Shapley Additive Explanations. Specifically, this code is using SHAP's force_plot function, which is a way to show the contribution of each feature to a single prediction in a force-directed layout. The shap.images function initializes JavaScript in the Jupyter Notebook environment to display SHAP plots in line within the notebook. The shap.force_plot function is then called to create and display the force plot visualization. It takes several arguments. 1. The base value, which is the model's output expected value when no features have been observed. The base value is obtained by taking the GRU_explainer.expected_value and transforming it back to the original scale with data_loader.inverse_transform. 2. The shap values for a specific prediction, which quantify the impact of each feature on that prediction relative to the base value. These values are again converted to the original scale using data_loader.inverse_transform. 3. The feature names that correspond to the SHAP values, for which the column names are obtained from data_loader.get_values.columns. If the comment after the code is to be considered, it indicates that an alternative way to get the feature names is feature_names equals data.columns. This force_plot will graphically represent the positive and negative contributions of each feature to the model's prediction, helping users to understand which features drive the prediction up or down relative to the base value. The code is for generating a SHAP, Shapley Additive Explanations, dependence plot, which is used to interpret the predictions of a machine learning model. This plot helps in understanding the relationship between a specific feature and the impact it has on the model's output. Here is a breakdown of what is happening in the code. 1. Shap.dependence_plot. This function call creates the dependence plot. The first argument 1 indicates it is plotting for the feature at index 1 in the feature set. 2. Data_loader.inverse_transform shap_values 0. This transforms the shap_values, which presumably have been computed on scaled or otherwise transformed data, back into the original feature space. The 0 index might be referring to the SHAP values for a specific class in a classification problem or for the output in a regression context. 3. Data_loader.inverse_transform sample. This transforms a sample of data back into the original feature space. This sample is then used for plotting individual data points on the dependence plot, which can highlight the distribution of the actual data. 4. Feature_names equals data_loader.get_values.columns. This argument sets the feature names for the axes of the plot according to the columns in the data frame or data structure returned by data_loader.get_values. In summary, the code uses SHAP library functions to visualize the effect of the second feature in the dataset at index 1 on the model's predictions by creating a scatter plot. The actual data is represented in its original scale, and the names of the features are accurately labeled using the feature names provided by the data_loader object. The given code snippet appears to be using the SHAP, Shapley Additive Explanations, library in Python to create a dependence plot for feature analysis and machine learning. The function shap.dependence_plot generates a visualization depicting the relationship between a selected feature and the SHAP values, which quantify the impact of that feature on model predictions. The 2 in the first argument indicates that the plot should be created for the third feature in the dataset, since indexing is 0-based in Python. This would show how the SHAP values for predictions change as this particular feature varies, providing insights into the feature's interactions and significance. Data_loader.inverse_transform shap_values 0 suggests that the original SHAP values corresponding to a set of model predictions, specifically the first class or output if it's a multi-class/output model, are being inversely transformed. This probably means that the SHAP values have been scaled or transformed during processing, and inverse_transform is used to convert them back to their original scale to make sense in the context of the original data. Similarly, data_loader.inverse_transform sample indicates that a particular sample of data is being inversely transformed for the same reasons as above, ensuring the visualization reflects the original scale and distribution of the data. Lastly, feature_names equals data_loader.get_values.columns is likely providing a list of feature names to the plot function so that the x-axis can be labeled with the appropriate feature names instead of default numerical indices. It helps in interpreting which feature the plot is actually describing. In summary, this code generates a SHAP dependence plot for the third feature in a dataset, after inversely transforming both the SHAP values and a sample of data for visualization purposes, with feature names provided for improved interpretability. This graphical representation helps in understanding how the given feature influences the model's predictions. The provided code snippet is initializing an instance of a LIME, local interpretable model agnostic explanations, explainer specifically designed for tabular data. This is done using the Lime Tabular Explainer class provided by the Lime library. The explainer is built with the following parameters: x_trained. This is the training dataset used to interpret the model predictions. It consists of tabular data with rows representing instances and columns representing the features. Mode equals regression. This indicates that the explainer is being used for a regression problem, as opposed to a classification problem. Feature_names equals data_loader.get_values. Columns. It sets the feature names using the columns from the dataset obtained through data_loader.get_values. Class_names sadface if specifies the names of the target variables being predicted. In this case, it is a single target regression with the target variable name if. Categorical_features sadface 0 indicates that the first feature, index 0, in the dataset is categorical. This allows the explainer to treat it appropriately by not assuming it is continuous. Discretize_continuous equals true allows for the discretization, binning, of continuous features, which can aid in interpreting the model by grouping continuous feature values into intervals. Overall, the purpose of this code is to set up an explainer object that can be used to generate human-understandable explanations for the predictions of a machine learning regression model. These explanations can help in understanding which features contributed to each prediction and how they affected the output. This Python code snippet performs several key operations primarily related to generating a visual explanation for a model prediction using Lime, local interpretable model agnostic explanations. Firstly, it selects a random sample from a dataset of test indices using NumPy's random.choice function. The test_indexes array presumably contains indices of test samples, and one index is randomly chosen to be the sample index, sample_idx, which is then printed out. Next, using this sample_idx, the code retrieves a corresponding sample, x_sample, from the x_test dataset. This sample will be used for explanation. Following the sample retrieval, the explainer object, which is an instance of a Lime explainer, is called to generate an explanation for the prediction made by a model, here denoted as GRU_model. The explain_instance method takes in the sample x_sample, the prediction function GRU_model.predict, and a parameter number_features set to the value of data_loader.lag to control the number of features used in the explanation. Finally, the created explanation is transformed into a visualization using as_pyplot_figure method, which creates a matplotlib figure. The figure is then displayed using plt.show from the matplotlib.pyplot library. The visualization provides insights into which features were most influential in the model's prediction for the given sample. The purpose of this code snippet is to perform operations related to data processing and transformation in the context of machine learning. Specifically, the code appears to be handling the shapes of test data and predictions, as well as applying an inverse transformation to training and testing data. Starting with y_test.shape, this part simply retrieves the shape of the test data set, which could be a number py array or similar data structure. Knowing the shape is useful for debugging or understanding the dimensionality of the data being worked with. The GRU_predictions 0 part of the code looks like it is accessing the first element of an array or list named GRU_predictions. This could be the first set of predictions from a model, likely a GRU, gated recurrent unit, neural network based on the variable naming. Moving on to the y_train_real equals data_loader.inverse_transform, y_train, lined. This indicates that an object data_loader is being used to apply an inverse transformation to the y_train data. This is typically done to reverse a previous transformation that was applied for the purpose of model training, such as scaling or normalization. The result is stored in y_train_real, which suggests that the real or original values of the training targets are being restored. Finally, y_test_real equals data_loader.inverse_transform, y_test, performs the same inverse transformation on the y_test data, restoring the test targets to their original scale or distribution. The transformed data is stored in y_test_real. Overall, the code is not a complete statement and seems to be partially copied. However, the individual fragments suggest operations associated with handling prediction results and preparing data for further analysis or model evaluation by inverting earlier applied transformations. The code involves two main parts: test_indexes, 1, smiley face, and y_test.shape. The first part, test_indexes, 1, smiley face, implies that test_indexes is an array or similar sequence-like object from which we are slicing all elements starting from the second element up to the last. The slice operation, 1, smiley face, omits the first element of the array. The second part of the code, y_test.shape, is a property call on an object named y_test which seems to be a numpy array or a similar data structure that has a .shape attribute. The .shape attribute returns a tuple representing the dimensions, i.e., the number of elements in each axis of the array. When these two expressions are combined with a comma in between, it can be inferred that the intention is to create a tuple where the first element is the shape of the resulting slice test_indexes, 1, smiley face, array, and the second element is the shape of the y_test array. This tuple might be used to compare dimensions of arrays or for information purposes to know the size of the test datasets. Presumably, this code is part of a larger context where the shapes of these arrays are critical, for instance in data processing, testing, or validation tasks. This code is likely used in the context of machine learning or data analysis, where y_test is a variable representing the test dataset's true labels or outcomes. The .shape attribute is a property associated with number py arrays, pandas series, or similar array-like data structures, and is used here to query the structure of y_test. When this code is executed, it will return a tuple describing the dimensions of the y_test array. For instance, if y_test represents a one-dimensional array of labels, the output could look like n, where n is the number of observations or labels in the test dataset. If y_test is two-dimensional, which could be the case for one-hot encoded labels or multi-output regression, the output would be n, m, where n is the number of observations and m is the number of distinct label categories or output features. This information is useful for confirming the size of the dataset before performing further operations, such as evaluating the performance of a machine learning model by comparing these true labels to the predicted ones, ensuring that the predicted outputs match the shape of y_test. This code seems to be Python code that involves reshaping operations on two variables, presumably arrays, named GRU_predictions and LSTM_predictions. However, there is a syntax error in the given code since it lacks any separator between the calls reshape, -1, .shape for each of the two variables. If we presume that the intention was to show the shape of each reshaped array on separate lines or with a valid separator, the code would be trying to reshape both arrays into two-dimensional arrays with one column each and then querying their new shapes. When calling reshape -1 on an array, the -1 tells number py to automatically calculate the size of this dimension based on the length of the array and the remaining dimensions. This operation effectively turns the array's GRU_predictions and LSTM_predictions into two-dimensional column vectors. The shape attribute would then provide the dimensions of these reshaped arrays, which would be useful for confirming the new structure or for debugging purposes to ensure that the arrays are in the correct form for subsequent operations, such as input into a machine learning model or comparison operations. For the code to function properly, it must be corrected with a separator like a semicolon or being split into separate lines for each operation. For example, Python GRU_predictions.reshape -1 .shape LSTM_predictions.reshape -1 .shape, or with a semicolon, Python GRU_predictions.reshape -1 .shape LSTM_predictions.reshape -1 .shape. Corrected like this, the code would output the shapes of the two arrays after they have been reshaped into column vectors. This code snippet is used to split the date column of a dataset into training and testing subsets based on provided indices. The data_loader.dataset date part accesses the date column of a dataset held within a data_loader object. The .iloc train_indexes and .iloc test_indexes parts use integer location-based indexing to select rows corresponding to the training and testing sets, respectively. The train_indexes and test_indexes are likely arrays or lists containing indices that have been determined to be part of the training set and test set. The result is two separate variables, date_train and date_test, which contain the date entries for the respective training and testing subsets of the data. This type of operation is typical in machine learning and data analysis workflows where a dataset is divided into distinct sets for the purpose of model training and evaluation. This code is a script that uses the matplotlib library to plot a figure illustrating the performance of different prediction models as compared with actual data. Specifically, the code creates a line plot with a size of 12 by 6 inches and plots multiple time series data on it. First, it plots the actual training close prices, y_train_real, as a blue dotted line, starting from an index offset by data_loader.lag. To align with the predictions which usually start after a specified lag period due to how time series models are trained. Then, it plots the actual test close prices, y_test_real, as a solid blue line. Following that, the script plots the predictions from a GRU, gated recurrent unit, model with the color green. It also plots predictions from an LSTM, long short-term memory, model, in red, and make sure the array is reshaped to match the needed dimensions. Lastly, predictions from a baseline model are plotted with an orange line. The plot includes a legend to differentiate among the plotted data series, and finally, the plt.show command is used to display the resulting plot on the screen. Hence, the primary purpose of the code is to visually compare the actual stock closing prices with the predictions made by GRU, LSTM, and baseline models for both training and testing datasets. This particular code snippet is used to evaluate and compare the performance of 3 different forecasting models: GRU, gated recurrent unit, LSTM, long short-term memory, and a baseline model. Each of these models has made predictions, and these predictions are being compared against the actual values, y_test_real, to assess how well each model performs. First, the code calculates the mean squared error, MSE, for each model by comparing their respective predictions, GRU_predictions_real, LSTM_predictions_real, baseline_predictions_real, against the actual values. MSE is a measure of the average squared difference between the actual values and the predicted values, indicating how close the predictions are to the actual result. Next, it computes the mean absolute percentage error, MAPE, for each model, which expresses the average absolute percent error between the predicted and actual values. This gives an idea of the magnitude of the prediction errors in terms of percentages. The mean absolute error, MA, is also calculated for each model, representing the average absolute difference between the predicted and actual values. This metric provides a straightforward measure of average error magnitude without considering the direction of the error. Finally, the code prints out the MSE, root mean squared error, RMSE, MA, and MAPE for each model, formatting the output to 2 decimal places. RMSE is simply the square root of the MSE and gives an idea of the error magnitude in the same units as the original data. By providing these metrics, the code enables a comparison of the model prediction accuracies. Lower values for MSE, MA, and MAPE indicate better predictive performance. The print statements format the report in an easily readable manner, laying out the comparative results for each of the error metrics across